Okay, the next topic is linear equations, determinants, and inverse matrices. Okay, so they say here we're taking a matrix and multiplying it times a vector. And we said that when we do that, we're going to get a new vector because this is like n by m, and this is n, or n by m, so this is m by 1. So you're going to get n by 1 as a result. So you're going to get something which is m by 1 is a vector. So the result is going to be a vector because of the 1. So we'll call that vector b. But this is an equation, and so it's saying that what's here is equal to what's here. And so what's here is ax, and what's here is b. And when we say that they're equal, we mean, as we said earlier, when we say two matrices or two vectors are equal, that means that they're equal element by element. Now here, this is a vector, and this is a vector. So the first element on the left is equal to the first element on the right, and the second element on the left is equal to the second element on the right, and so on. Well, the first element on the right, the second element on the right, third element, those are here. And so, but this, when you multiply this out, as we said, we're going to get a vector, and the first element of this vector is going to look like this. So you can check that out for yourself, but it's true. So the first element of this vector should be equal to the first element of this vector, and that's what this says. This element is equal to the first element of b, and this will be equal to the second element of b, and so on. So this is the same as this. But this, of course, we can view as a system of equations, and these are linear equations because there's no square on x1, there's no square on x2, there's no square on x2 anywhere, and so on. So these are linear equations. So this is a system of linear equations. How many are there? Well, how many elements are there in B? In B? Well, I think we said that B is going to be m by 1. So there must be m of these. So there's m equations. And then how many variables are there? That is going to come from the number of columns of A. Because we're going to take the first column of A times the we're going to take the first row of A times the first column of X. Well, there's only one column of X, but anyway, times the first column of X. So the number of columns of A and the number of rows of X, we already said they have to match, and that is going to be, as somewhere we said, n. So there's going to be n of these. So across here, there's going to be n terms. By the way, in math, we use the word terms when things are separated by a plus sign, and we use the word factors when things are separated by a multiplication sign. So I can say there are, what did I say? N terms here. And we already said there are m rows. So we have m equations, and each equation has, on its left-hand side, has n terms. So again, A is m by n, and that this m, if we have to go through this m is the number of rows of this system of linear equations, and this n is the number of terms on the left-hand side of each of these equations. Okay. Now the next thing here I think is not true actually. I haven't thought about it completely, but it looks like it's wrong to me. A necessary condition for such a set of equations to have a unique solution is that m equals n. So he says that m has to equal n, that is the number of terms here, and the number of equations have to be the same, but I don't think that's right. But anyway, I'm not going to go think about that too hard, but I'm pretty sure that's wrong. Anyway, let's just read what it says. A necessary condition for a set of equations to have a unique solution is that m equals n, i.e. it's a square matrix. So he's saying it has to be a square matrix. I don't think that's true. But anyway, let's just go on from there. Okay, so now he talks about the determinant, which he hasn't explained what it is yet. But I guess, again, we're assuming that this is a review. So in case the determinant of the matrix A, what matrix A? This matrix A, is not equal to 0, the matrix is called non-singular. And in that case, the inverse matrix, or A, has an inverse. Now again, he hasn't explained what the word inverse means yet. But again, I guess this is just supposed to be a review. So as a review, let's say that we know what determinant means, and if the determinant is not 0, then A has an inverse. And now, after that, he explains what he means by inverse. So what do we mean by the inverse? This is a symbol for the inverse. What do we mean by it, though? We mean the matrix here, that this is a matrix. It's a symbol for a specific matrix. And it's what matrix, what specific matrix is it? It's the matrix which, when we multiply times A, gives us I, gives us the identity element. And that's basically similar to what we mean in regular arithmetic when we have the inverse of 5. Oftentimes we'll say the inverse of 5 is 1/5. And what can we mean by that? We can say we can mean that 5 times 1/5 gives you 1. So 1 in that statement is the equivalent of I in this statement. And 1 is also called an identity element, and I is called an identity element. 1 is called the identity element for multiplication between numbers, and I is called the identity element for multiplication between matrices. Okay, anyway, so going back, this is what we mean by the inverse, that when you multiply it times A, you get I. Okay, so here he says, this is a little bit off also. Maybe this is because English is not this person's native language. I think that's a Dutch person. Anyway, they say a set of linear equations represented by ax equals b thus has a solution. But yes, he should be saying has a solution if the inverse exists. He didn't say that here. But anyway, a set of linear equations represented by ax equals b thus has a solution if the inverse exists, or if the determinant is not 0. And the inverse, and the solution, will be A inverse B, because you can see that going to here, if A has an inverse, then you can multiply the inverse, put it over here, and put it right here. So if you multiply, put the A inverse here times A, you just get the identity element. And then if you have the identity element and you multiply times x, you just get x. That's the point of the identity element. You just get x, and then we said we're going to multiply this side right here by A inverse, so that's what they have here. So if the inverse exists, or we can say if the determinant is not equal to 0 of A, then the solution, this has a solution, and the solution is given here, A inverse B. So this, you want the solution, it's A inverse B. So you might want to solve this, and you could do this, but he warns us or suggests that we don't do it that way. He says, please note that solving a set of linear equations by calculating the inverse matrix, which, basically, when we have this system of linear equations, we said that we can write it like this, and then we can get the solution to this like this, which basically means we've solved the system, right? Because if we know what the x vector is, that means we know what x makes this true. What x1, x2, x so on makes this true. So that's exactly what we're trying to find out. When we solve a system of linear equations, we want to know what x's make it true. And here we have a formula for the x's. So we will have solved the system of linear equations, but he sort of warns us against doing that this way. He says, please note that solving a set of linear equations by calculating the inverse matrix is not a wise thing to do. Better ways to solve such systems are known and available in most linear algebra packages. So there are easier ways to do it, apparently. Okay, the next thing we go to is vector norms, inner products, and orthogonality. So the norm is basically just an extension of the idea of the absolute value, or like the size, right? The absolute value is kind of the size of something, and the norm is basically some way to talk about size of a vector. Of course, we can talk about the number of elements in the vector, but that's not what they mean by the norm. It's more to do with what are the values in there, and some way to sort of summarize those values. And the inner product will be used to help us get the norm, and it has other uses as well. And orthogonality just means when we have this notion, of course, of perpendicularity. The two lines are perpendicular, and it's kind of a generalization or extension of that idea for vectors, and particularly vectors, that are more than just 3 dimensions. We still have some way maybe to say that they're perpendicular even though we can't see them. So if we think of a vector like a 2D vector, we can think of it as an arrow, then obviously it has a length. And what is that length? Well, we talked about if we use the Euclidean definition for length, but that's not always the most appropriate way to measure the length, because if you're a taxi driver in a city like Manhattan, that length is sort of not that relevant. A more relevant length is the distance it takes you to get from one point to another. Usually you have to go sort of like on the sides of a triangle or something like that. So anyway, but if we use the regular idea of length, it's this idea. Now this assumes that the vector originates at the origin, but vectors don't necessarily originate at the origin, but this sort of works the same way. So anyway, this is the length, and we use the symbol for it. And if we had a vector, an arrow in 3-dimensional space, we just have one more term here. We'd have x1 squared, x2 squared, x3 squared, and the square root of that. So you can see that we might generalize that. If we had a vector in R4, we could make it x1 squared, x2 squared, x3 squared, x4 squared, and we could do that for R5 and so on. And the inner product, which might be sometimes denoted with this symbol, is defined to be the norm of x, and remember that's going to give us a scalar, right? The norm gives you a scalar. This is all scalar stuff over here. And the norm of y is a scalar times the cosine of the angle between the two vectors. And by the way, here they're using this word orthonormal basis, we've talked about the fact that basis vectors don't have to be perpendicular, but if they are perpendicular, they're called orthonormal. Actually, I believe orthonormal means that they're perpendicular and have unit length. So, two vectors don't have to each have unit length to be perpendicular, but we scale them down to unit length, and then we call them an orthonormal basis, or a set of orthonormal basis vectors. And here we've defined what we mean by the inner product. Now you might recall that we also say that the dot product is equal to this. And so if we have said in the past that the norm is equal to the square root of the dot product, and since this is another way to write the dot product, we can also say that it's the square root of the inner product. And this is not written too clearly. In the case that the angle between two vectors should say two vectors x and y is 90 degrees. The vectors are orthogonal, and in that case the dot product is equal to 0, and that we can see that over here because this is the dot product we just said. And the cosine of, if they're perpendicular, the cosine of the angle between them is 0, so this will be 0. So that so xt, which is just like the dot product, is equal to 0. Okay, we have another definition, an orthogonal matrix. So what does that mean? Orthogonal matrix. Right? That doesn't seem to make any sense, right? Things are orthogonal if they're perpendicular. There's only one matrix here, so it sort of doesn't make sense to talk about an orthogonal matrix. You might be able to talk about something like orthogonal matrices, like two matrices are orthogonal, but that's not what they mean here, actually. So what do they mean by the word orthogonal matrix? So it's kind of a weird way to describe this particular matrix, but what it means is if the columns are orthogonal, or actually orthonormal. So anyway, let's just say if the columns are orthogonal, then it's called an orthogonal matrix, but we have to say a little bit more. If the columns are not only orthogonal, but they're all of unit length, and we know what we mean by length here. This is what we mean by length. So if you take a column and it's of unit length, and if each of those columns is orthogonal to each of the other ones, then that matrix is called orthogonal matrix. So maybe not the best name for this, because orthogonal matrix makes you think, oh, somehow it's perpendicular to something, but that's not what it means. It means that the columns are perpendicular to each other. Okay, but anyway, an orthogonal matrix, and we didn't talk about this, but an orthogonal matrix has an interesting property, and that is that it preserves the length, or the norm, of vectors. What does that mean? It means if you take a vector and you multiply it by an orthogonal matrix, you will of course get a new vector out, but one thing that will happen if the matrix is orthogonal is that the length of the output of this new vector, in other words, the length of that will be the same as the length of the original input vector. So in other words, here, okay, this is a mistake actually. This x and this x should not be the same. That's too bad. But I suppose what he meant to say is that ax, so you have, no, I'm sorry, it is true. So ax That's the output. The length of that, the norm of that, is equal to the length of x. So um, by multiplying by a, the length of that is just the length of the original x. And then there's one more property about orthogonal matrices, and that is that the inverse and the transpose are equal. So that kind of makes life super nice. What do I mean by that? Well, oftentimes we would like to find the inverse of a matrix, but it's a lot of work to find the inverse of a matrix. Well, maybe it's not a lot of work if you ask the computer to do it, but it's a lot of work in general to do it. But here it says if you happen to have an orthogonal matrix, it's not a lot of work at all. All you have to do is basically flip the matrix, and that will give you the inverse.